Okay, so yeah, let's start with number 8 from first law. Yeah. Oh, uh, I don't know what's going on there. Let's see. Let's start with uh, first law, number 8. Um, so air is contained in a piston cylinder system. The piston is connected to a spring. The air changes volume slowly. What that means, this quasi-equilibrium thing, means that at every instant, you can assume that everything's in balance. Okay, so you can balance the forces at every instant. Um, and it changes from 0.003 to 0.002. Okay, so let's think about instant 1 and instant 2. Um, the volume at instant 1 is 0.003 cubic meters. The volume at instant 2 is 0.002 cubic meters. Cubic. Is that a specific volume or a true volume? Yeah, and you can tell from the units, and I mean, I wrote it as a capital V, but you can tell from the units. The spring force varies linearly, so we're going to use that, and it goes from 900 newtons. So we'll say the spring force is 900 newtons at instant 1 and 0 at instant 2. And the area of the piston face is 0.018 meters squared. And the atmospheric pressure stays the same. Okay, so so first we're going to think of like a free body diagram of the piston. And there is a pressure inside. So I'm thinking of this system like this, where here's the piston, here's the gas that's our system. The spring force is pushing down like this. And there's atmospheric pressure outside. So at instant 1, move this down a little. So this is instant 1. We have the pressure from the gas pushing up. We have atmospheric pressure. And okay, pressure is not a force. So let me change this to a force. So we have the gas pressure times the area of the piston, which is 0.018, pushing up. Pushing down, we have 100 times 10 to the third pascals times that area. And then we have the spring force of 900. And so Newton's second law, assuming that this is balanced at this instant, we have that 0.018 P is equal to, well, let me write it in the form of Newton's law first. So I'll call up positive. So this is up. Down is 1, 2. So that is just so shoot times 10 to the 5, 1, 2, 3, 4, 5. So I think that's 1800. And then we have minus 900 is equal to 0. So 0.018 P is equal to 2700. Can someone divide both sides by 0.018? And that'll give us the pressure of the gas at instant 1. I mean, do it and then tell me what it is.
150,000.
Okay. So that's about, well, that's 1.5 times the atmospheric pressure. This is pascals. And then at instant 2, we have no force from the spring, so it's just a downward force of 100 times 10 to the third times 0.018, and then pushing up, we just have P times 0.018. And if you go through Newton's second law again, you just get that P here is equal to the atmospheric pressure, because there's nothing else going on there. So those are the pressures of the gas at the 2 instants. Okay, so now we are going to assume that this pressure varies linearly with the volume. So what we're trying to figure out is W for the gas. So the work of expansion. So we're trying to use this integral. It's going to go from the starting volume to the ending volume of P dV. Okay. And we just want a linear function where P goes from 150,000 to 100,000. So we can say, let's say P, okay. Assume P is linear with volume. Okay, so I'm going to think of P as M volume plus B, and I'm going to fit it to those 2 points. So P1, 150,000, is equal to 0.003 M plus B. This is instant 1. And then in instant 2, my pressure is 100,000, and that's equal to 0.002 M plus B. So if we subtract this equation from the top equation, we get that 50,000 is equal to 0.001 m. So m is equal to 50 times 10 to the 6, I think. And now we can plug that into either one of these equations to get b. 150,000 is equal to 0.003 times 50 times 10 to the 6 plus b. Can someone tell me what that b is? B is 0, okay? So the pressure then, as a function of the volume, which is what we need in order to compute that integral, the pressure is 50 times 10 to the 6 V, and that's it. Any questions about coming up with that linear relationship? And now we can go to the integral. So the work of expansion is equal to the integral from 0.003 to 0.002 of 50 times 10 to the 6 V dV. And so that is 50 times 10 to the 6 V squared over 2. So 25 times 10 to the 6 V squared from 0.003 to 0.002. And so we got 25 times 10 to the 6 times 0.002 squared minus 25 times 10 to the 6 times 0.003 squared. Can someone calculate that for me?
Negative 125 joules.
Say it again. Negative
125 joules.
125 joules? That's so little. I mean, okay. We're multiplying by a tiny thing squared, so let's go with that. So does it make sense that that comes out negative?
Yes.
Yes, because the volume decreases. So there you go. Any questions about that? All right. Anybody want to see any other homework questions? All right, so we've been talking about the first law. And it says that the change in the energy of the system is equal to the heat added to the gas minus the work done by the gas. And now we're going to look at this in a new form, the differential form of the first law. And this expresses the first law in terms of rates of change. So in terms of rates of change, the time derivative of the energy of the system is equal to Q dot minus W dot. This dE dt is just the time derivative of all of those things that make up the energy. So that's d kinetic energy with respect to time plus the derivative of the potential energy with respect to time plus the derivative of the internal energy with respect to time. This is usually the one that we care about the most, just like with the regular first law. And the definition of Q dot is the rate at which heat is added to the system. And W dot is the rate at which work is done by the system. Okay, so notice that we're going to be using the same sign convention as for the regular first law. Let's call it the standard first law. So if energy is added to the system by heat, Q dot is positive, and if work is removed from the system and added to the surroundings, W dot is positive. And you want to be able to rattle off these definitions. Having these definitions at the front of your brain is important for being able to think through these problems. We'll use this differential form of the first law in two types of problems. The first one is called steady state. And this is something we're going to use for the rest of the semester, this idea of steady state. So be sure that you're clear on what this means. Through the whole class, steady state means no properties change over time. Okay.
Like that rest or
Well, so like if you set your oven to 425 degrees, there's a period where the temperature is changing over time as it gets up to the temperature. And, if your oven was sealed or whatever, the pressure would be changing and whatever. But once it gets up to 425 degrees, the temperature stays constant, the pressure would stay constant, then you're at steady state. So we're kind of breaking it up into the two phases, the transition from one state to another, and then the rest of the time the state is constant, whatever is going on. Yep.
What do you mean, like, when you say through the whole class? Is this like a simplification?
Well, it's just something that, like, if you're designing an engineering system, you don't like imagine something that generates heat as it runs. Say you have a pump or something, and the motor creates heat. Well, you don't. It's not going to last very long if it's going to keep the temperature is going to keep rising throughout its whole run. So, for example, like you plug it in, it starts going, the temperature will start rising, but at some point that rising temperature will stop, and at that point this thing is operating in steady state. Okay, so that's what I mean. We're talking about not the transition from cold to running, but once it's running, most engineering systems are going to maintain their properties. Um, okay, so if no properties change over time, that energy, capital E, is a property. And so the most important thing for the first law is that dE dt is equal to zero. There's no change at all over time. The other case, which is more difficult for calculations, is the transient case. And this is when properties do change over time. And so in this case, dE dt is non-zero. Um, this isn't the only reason that we're going to use the differential form of the first law, but one of the major reasons we'll use it. So often, the differential form of the first law is going to be used with heat transfer equations. So now we're going to talk about heat transfer equations, and all of them are given in terms of a Q dot, the rate that heat is moving, from one place to another. Energy is moving from one place to another by heat. For all of you who are going to major in mechanical engineering, you'll take a full class in heat transfer. So obviously what we're doing here is just kind of a simplified introduction, But so now we're going to spend the rest of this class, maybe a little of the next class, talking about heat transfer. There are three modes of heat transfer, three ways that heat can be transferred. By the way, can anyone come up with a definition of heat? This is such a quizzy question. This is the kind of thing that could go on a quiz more than once this semester. It is energy transfer, and it's a specific kind of energy transfer. It's yeah, that would get full points on a quiz. So it's energy transfer that's the result of temperature differences. Okay. Whereas work is also energy transfer, but it's due to what? Application of forces. Okay. Yeah. And it's mechanical. Um, okay. There are three modes of heat transfer, three ways that energy can be transferred due to temperature differences. Um, these are conduction, um, I guess the next one I do is radiation, and third is convection. Um, conduction is like an example of that is a pan handle getting hot. So when you put a pan on the stove, you don't have the handle directly over the flame of the stove, you know. But if you leave it on there long enough, uh, the handle is going to get hot. And it's just because uh, the high temperature at the cooking part of the pan starts to spread out through the material. Okay, so it's that spreading of material, spreading of temperature through the material, spreading of energy through the material. Radiation, the best example of that, I think, is that's how we get energy from the sun. Um, we can't get heat from the sun through conduction because most of the distance between the sun and the earth doesn't have any material. There's no way for heat to transfer from molecule to molecule. There are no molecules of anything. Um, so this is energy transfer from the sun. And then convection is energy that's moved by a fluid from one place to another. So um, if you have a uh, if you have a hot spot in water and that water is flowing, once the water gets here, it's going to have taken some of that energy with it. Uh, a good example of convection is wind chill. Well, in a way, it's kind of like the wording is kind of misleading. Uh, there's no such thing as coldness moving from place to place. There's only such a thing um, as energy moving as high temperature. Uh, so energy only goes from high temperature to low temperature. So you can't. So it's really not a wind chill. It's that as uh, a high temperature fluid that has a lot of energy moves, it's transferring, losing that energy to this spot, and then it moves, and then it's losing it to this spot, and then it's losing it to this spot. Okay.
Professor, is it like radiators? Radiator, like car radiator?
Let's see. Yes, exactly. Like the inside of a radiator. Yes. So the fluid moves through the radiator, absorbs all that energy through conduction, and then it carries the energy away in the fluid through convection. Yep. Okay, so I'm going to talk about conduction first.
Professor?
Yeah.
So like in terms of stoves, like a gas stove, because the natural gas is
Mm-hmm.
the thing that's getting hot, it would be convection? Or
Well, let's see. I mean, I guess all three are happening almost all the time, just in uh, different amounts. Um, convection. Think about the importance of convection as like would would this thing still work if the fluid wasn't moving? You know, a stove. I mean, I guess it needs the fluid to move from the fire up to the pan, but it's not very far, you know. There's also some radiation that's happening. Uh,
And for induction, like the magnetic one, that's like basically the work is just being done to the pan and the heat is made there.
Yeah, mostly the pan is the molecules on the bottom of the pan are initially heated up, you know, and then there's high energy at the bottom of the pan. And then if you think of energy as vibrating molecules, those vibrations start to cause higher vibrations next to it and next to that and next to that. And so without the molecules actually moving, those vibrations spread. And in that way, energy spreads.
Thanks.
Yep. Okay, so in conduction, energy is transferred through material particle to particle. Um, without the particles changing their locations. So that's the key difference between this and convection. Um, and with every one of these, I'm going to point out the dependence on material. So conduction requires a medium to transfer through. So if your pan somehow if there was a section of your pan that had an absolute vacuum of molecules, then that would end the conduction. There would be no conducted heat past that point of no molecules because there'd be vibrations at the bottom that would cause vibrations next to it. But once you get to empty space, those vibrations can't vibrate anything, you know? So there has to be material all the way along the path for conduction to take place. Okay.
Like a thermos?
Yeah, that's what a thermos tries to do. Yeah, exactly.
That doesn't work because there is, air molecules in space, or is it just mainly like
Yeah, just various kinds. I mean, they try to use kinds that allow very little conduction, and often depending on the type of thermos, they try to take advantage of vacuum, the fact that it can't transfer through a vacuum, but there has to be some material there, you know. So conduction, you can't get conduction across space from the sun to Earth, because once the vibrating particles get to the emptiness of space, there's no more path of vibrations that can happen. The equation for conduction that we're going to use is Q dot, so that's the rate of heat transfer, is equal to, and I'm first going to write this in the form that you would always see it written, negative Greek letter kappa times A times the temperature dx. And the first change I'm going to make to this is that negative is always I'm going to keep that on the equation sheet that I give to you and everything. But the first thing you should do is ignore that. Okay. That negative is just a direction. And the best way to think about the direction is energy flows from high temperature to low temperature. these different constants and things. Kappa is called the coefficient of thermal conductivity. Um, Copper has a high coefficient of thermal activity. Plastic has a low coefficient of thermal activity. Um, and the SI units of this are watts per meter Kelvin. And watts are joules per second. So that's a connection that we're going to use pretty often.
Is the coefficient going to be given to us?
Okay, yes. So for that's something you can Google or I'll give it to you in problems or whatever, but it's specific to the material. Yeah. Uh, I don't know if you've ever thought about this before, or maybe it's even been brought up in a class. But if you're ever trying to figure out the units for some crazy constant or something, you know, a lot of times scientific constants have just weird combinations of units. You can always do it like this. If we know the units of everything else in the equation, okay, so uh, let's relate each of these to their SI units. The rate of heat transfer is joules per second. And I'm in this equation, I'm just replacing each variable with its units. I'm using SI units. We're trying to figure out the units for kappa. Area is meters squared. And the derivative of temperature with respect to X is units of Kelvin per meter. And so we can start canceling some stuff, isolate kappa, and we get kappa is equal to joules per second over meters Kelvin. Joules per second we can replace with watts. And so there's the SI units for that constant. So that's just a nice, simple little way to figure out the units on complicated things. If somebody is like, what are the units of the gravitational constant? Write out the equation that it appears in, replace each variable with its corresponding units, and you can figure out the units of the constant that way. Um, One thing that this is important, this is for conductivity and it's for the other types of heat transfer too. Um, you can't trust the sign from the heat transfer calculation when using it in the first law. So in every case when you use these heat transfer equations, you have to think about the direction that heat is traveling, that heat is going to transfer. It's always going to go from high temperature to low temperature. And then you have to think about that in terms of what's your system and what's the surroundings. Okay, so let me do an example. First let me draw a picture sort of how this works. So if you're talking about heat transfer going this way, through this, say that's a cylinder of material, then this cross section is the area. And this distance is the x. One thing that we're always going to do to simplify this is we will always have a linear relationship between temperature and x. Which means that we can always just replace the dt dx in that heat transfer equation with a difference equation where we just take the difference in temperatures and divide it by the total length between the two endpoints. Okay. That's the kind of thing when I said you'll take a full semester class in heat transfer, that's not generally true, that there's a linear relationship between temperature and x. And if it's more complicated, then you have to do this as a differential equation and the math gets a little uglier, you know. But okay, so we don't have time to do this right now, but I'm going to write out the example problem that we're going to start with next time. And you can sort of, if you want to try to think your way through it, see if you can make sense out of it. So let's say we have this window. And on this side, let's say we have 15 degrees Celsius. So this window is connecting, say, the inside of a house to the outside of the house. On one side, the surface has one temperature. On the other side, it has another temperature. On the back side, the temperature is 20 degrees Celsius. The dimensions are 1 meter by 1 meter. And the thickness is 2 centimeters. So let's say that this glass has a coefficient of thermal conductivity of 1.05 watts per meter Kelvin. First, if the temperature varies linearly with x, like I said, we always will have, calculate Q dot. And then second, if the system that we're isolating, our system, is the 20 degree Celsius side, you could think of that as like on a cold day, this is inside the house. What's the Q dot that you would have to use for the differential first law? Okay. That's it for today.